Let's now imagine that you are in a place where the darkness is so complete that you can't see anything, not even with a telescope. Close your eyes and visualize yourself in the Boötes supervoid, an immense sphere in space that could swallow our Milky Way millions of times over. Surprisingly, in this vast void stretching 330 million light-years, we would expect to find thousands of galaxies, but there are only 60. In 1995, Bob Williams, the director of the Hubble Space Telescope, after billions of dollars invested, detected a nearly tragic flaw in the system's optics. The first images, which were supposed to be perfect, were all blurred due to an error smaller than 1/50th the width of a human hair. A manned mission corrected this minor yet significant error by precisely adjusting the mirror. Then, under pressure to show results that justified the investment, Williams did something unexpected. He decided to point the Hubble at absolutely nothing. That's right, he overlooked planets, stars, and galaxies, and fixed the Hubble on a tiny piece of the sky, just 1/30 of the diameter of the Moon. For 10 straight days, the telescope stared at what seemed to be complete emptiness. And then, the unexpected happened. In that small fraction of the universe, where previously nothing was seen, the advanced technology of Hubble began to capture photons from distant galaxies. Slowly, forms began to emerge from the darkness, like ghosts from a distant past, in a variety of sizes, shapes, and colors. These were not just any galaxies. They were the farthest and oldest we had ever seen, some so ancient they showed us what the universe looked like billions of years ago. The resulting image, known as the Hubble Deep Field, is not just a photo. It is a time capsule that captures the vastness of an ever-expanding universe. When we look at the Sun, we are seeing it as it was about 8 minutes ago. This is practically instantaneous compared to what comes next. Moving a bit further, we find Andromeda, our neighboring galaxy. The light we see from Andromeda today started its journey 2.5 million years ago, at the time when the first human ancestors began to walk the Earth. Seems like a long time, doesn't it? But for the universe, it's just a blink of an eye within its long lifespan of 13.8 billion years. But how do we know the distance and age of these galaxies? A fascinating method is used, which is quite similar to the effect we hear when a fire truck siren passes by us. As the truck approaches, the sound is higher because the sound waves compress. As it moves away, the sound becomes lower as the waves expand. With the light from galaxies, something similar happens, but instead of sound, we observe colors. Imagine a galaxy as a gigantic luminous siren. If this siren is moving away from us, its light stretches, and what was blue becomes red, a phenomenon we call redshift. And just as a siren has its specific tone, certain chemical elements in a galaxy emit light at very precise frequencies. By observing how much this light shifts, we can determine the speed at which the galaxy is moving away from us. Moving even further in time and space, with the help of the James Webb Space Telescope, we can glimpse galaxies so ancient they existed just a few 100 million years after the Big Bang. But what if we could go even further? To a point in time where there was no visible light, where the universe was enveloped in complete darkness? This brings us to the period called the Era of the First Stars, a time so remote that even the powerful James Webb cannot show us. In the early days, the universe was a boiling cauldron of matter and radiation, where light could not travel freely, trapped in a dense and superheated plasma. But as the universe expanded, it cooled, and the density of radiation fell more rapidly than that of matter. After about 380,000 years, things began to change. Atomic nuclei could finally join with electrons to form simple atoms, and light was free to travel. It may seem like a story of freedom, but make no mistake, there were still mysteries hidden in the shadows, such as dark matter. Discovered in the 1960s and 1970s by scientists like Vera Rubin, dark matter is this enigmatic substance that does not interact with light, but has a strong gravitational influence. It makes up about 80% of the matter in the universe, and its presence is essential to keep galaxies together. However, unlike ordinary matter, it cannot form stars or planets, because it cannot lose energy by emitting radiation. Dark matter, this enigmatic component that makes up most of the universe, remains invisible because it does not interact with light. It does not emit, reflect, or absorb light, but its presence is felt through the gravitational force it exerts on galaxies and stars. This is the great paradox of the universe. What is abundant remains hidden, and what is visible is just a small part of the cosmic story. Let's give an example by comparing it to the ocean. When you dive into its crystal-clear waters, you are greeted by schools of colorful fish. But as you descend deeper, the sunlight disappears, and the world becomes a monochromatic place until you reach a point where darkness is total. Yet, marine life not only exists, but adapts and thrives. Interestingly, redfish become almost invisible, as red light does not penetrate at that depth. Thus, the first hydrogen atoms began to form, but they were often undone by extreme conditions, turning the universe into a vast sea of ionized plasma. The transition to a state where atoms could exist stably was a gradual process, marking the end of the Dark Ages and the beginning of the era of reionization. The first stars played a crucial role, but were not enough to ionize the universe completely. It was the first galaxies, with their long-lasting stars and active black holes, that finally turned on the lights, allowing light to travel freely through space. In 1944, in a world still turbulent from war, Jan Oort and his student Hendrik Christoffel van de Hulst embarked on a revolutionary astronomical mission. They set out to unravel the secrets of the Milky Way, not through the stars that shine at night, but through the invisible hydrogen gas that fills the vast spaces between them. Let me give an example to clarify what they discovered. Imagine you are in a completely dark room and cannot see anything around you. However, you have a flashlight that emits only a specific color of light, say red. Now, suppose this room is filled with transparent balloons that can only be seen when illuminated by this red light. As you turn on the flashlight, you cannot see all the balloons at once, but as you move and the light reaches different parts of the room, the balloons become visible. Transferring this scenario to the context of the text, think of hydrogen as these transparent balloons filling the space between the stars. Visible light, like the light from a normal flashlight, cannot reveal the presence of hydrogen as it is transparent to these frequencies. However, Van de Hulst discovered that hydrogen emits a special light, a photon with a frequency of 14x20 megahertz, corresponding to a 21 cm radio wave, when there is a change in the spin of an electron. This specific emission functions like the red light of the flashlight, revealing where the hydrogen is. Radio telescopes are like the special flashlight that can detect this 21 cm radio light, allowing astronomers to see hydrogen in the universe. As the first stars begin to form and emit their own light, they ionize the surrounding hydrogen, which changes the way hydrogen emits its radio light. This creates bubbles in this field of hydrogen, similar to the balloons that become visible under the light of the flashlight. By observing how these bubbles appear, grow, and merge, astronomers can better understand the processes that were occurring in the young universe, in its critical early stages of star and galaxy formation. And why was this small change so important? This radio wave could map the hydrogen permeating the entire Milky Way, revealing the hidden structure of our galaxy, far beyond what the stars could show us. It was like having a new pair of eyes, capable of seeing beyond the veil of visible light. The audacity of Oort and Van de Hulst was matched across the ocean, where American scientists, led by Harold Doc Ewan and his advisor Edward Purcell, also pursued this theory. Ewan, using a handmade radio antenna hung from a laboratory window, captured the first 21 cm emission line on Easter morning in 1951. And so, a new era in astronomy began. This discovery not only proved that the Milky Way had a spiral structure, but also that it was rotating, a fact that had been merely speculated until then. Today, radio telescopes still search for this spectral line, exploring farther into space, uncovering new details of our galaxy and beyond. This primitive gas, following the trail of enigmatic dark matter, played a crucial role in the formation of the first stars and galaxies. Have you heard of the EDGES project? It's a bold attempt to capture signals from the earliest phases of the universe, even in the face of nearly insurmountable challenges. The signal we seek is incredibly faint, practically a needle in a cosmic haystack, obscured by the radiation from our own galaxy. But why do we persist in this search? Because understanding the birth of the first stars could tell us more about our own origins and the mysteries of dark matter, which, despite its enigmatic properties, seems to have played a crucial role in the formation of the first cosmic structures. In the vastness of the Murchison Desert in Australia, astronomers have set up an incredible array of antennas, including the famous Murchison Wide Field Array. These antennas, dubbed the ear that listens to the sky by the local indigenous people, are capturing the nuances of the radio waves of the primordial universe. And not far away, the ambitious Square Kilometre Array project is preparing to take this search to another level, with the ability to detect signals so weak they would be like hearing the buzz of a mosquito at a rock concert. Imagine a telescope so powerful that it could pick up a radar signal from an airport on a planet 10 light-years away. That is the promise of the Square Kilometre Array, which will peer directly into the first billion years of our universe, crossing the epoch of reionization into the mysterious Dark Ages. However, even the most remote places on Earth still suffer from human and atmospheric interference. That's why scientists are already thinking beyond, planning to install antennas on the far side of the Moon. Yes, you heard that right. The Moon. Using it as a natural shield against Earth's radio waves, we could finally have the clarity needed to illuminate the shadows of the cosmic Dark Ages. But that will be a topic for another video. Thank you for watching this far. Don't forget to like and comment on which topics you would like to see in our upcoming videos.